This is lecture 6, Artificial Starting Solution for IE 3340, Operation Research. In this lecture, we are going to discuss how to find a starting solution for certain problems in linear programming. As we saw in one of our previous lectures, in which we learned how to apply the simplex method. For those problems that we already discussed, it was very easy for us to find an initial solution. For all those problems, the initial solution was provided by the slack variables. However, that's not always the case. It's not always the case that we have a slack variables that can provide us with an initial solution for us to implement the simplex method. So in this lecture, we're going to discuss for those problems in which we don't have an initial solution, how to create an initial solution for us to implement the simplex method and solve the linear programming model. So the learning objectives for this lecture is to use the simplex algorithm to solve linear programming models involving equalities and or greater or equal constraints. So as I mentioned already, in those problems that we discussed in lecture 4, all those problems had an initial solution that was provided by slack variables because the constraints that we were dealing with were less than or equal constraints. So we were putting those problems into standard form by adding slack variables. Therefore, for us was very easy to find an initial solution. When we set up the tableau, that initial solution was given by S1, S2, S3, right? So when you deal with constraints that had an equal sign or greater or equal to constraint, the slack variables are not available for us to generate that initial solution. So we're going to discuss two methods that can help us generate that initial solution so we can implement the simplex method or the simplex algorithm. So the agenda for today is discuss the artificial starting solution. And then after we discuss what the artificial starting solution is, we are going to discuss the M method and the two-phase method to find that initial solution. So in this video, we're going to cover the M method. In the next video, we're going to discuss the two-phase method. Okay, so what is an artificial starting solution? So in the first 3 weeks, we focus on modeling LP, solving two variables, LP graphically, and lately, in the past few weeks, we've been talking about how to solve these linear programming models that have more than two decision variables using the simplex method or using the computer. However, linear programs in which all the constraints are less than or equal to with non-negativity right-hand sides offer a convenient all-slack starting basic fixable solution. However, models involving equalities and or greater or equal constraints do not. The procedure for starting linear programs with equalities and greater or equal to constraints is to use artificial variables that play the role of the slacks at the first iteration. The artificial variables are then disposed of at a later iteration. Two closely related methods are introduced in this lecture, the M method and the two-phase method. So let's talk about the first method, which is called the M method. The M method starts with the linear program in equation form. If equation I does not have a slack variable, an artificial variable Ri is added to form a starting solution, similar to the all-slack basic solution. The artificial variables are not part of the original problem. This is just a modeling trick which is needed to force them to zero by the time the optimal iteration is reached. So we are going to use these artificial variables. They're not part of the problem. This is just a modeling trick for us to get an initial solution for our problem. Those artificial variables are going to be discarded at the end by using a modeling trick, which I'm going to show you in this lecture. The desired goal is achieved by penalizing this variable in the objective function using the following rule. So the penalty rule for the artificial variables is given m. M is going to be a sufficiently large positive value. Mathematically, this m value will go to infinite. The objective coefficient of an artificial variable represents an appropriate penalty if the artificial variable objective coefficient is equal to minus m in maximization problems or positive m in minimization problems. So the idea is to use these artificial variables in the constraints. And we are going to penalize those artificial variables in the objective function by giving them very big values. So for example, if you're maximizing, let's say you're maximizing profit, in the objective function, we are going to subtract the artificial variable, and we are going to multiply that artificial variable by a very big negative value. So, we are going to multiply by a very large m value, and we are going to subtract that from the profit. So the idea is, since we know that this minus m times the artificial variable is going to go against our objective of maximizing our profit, we want those artificial variables towards the end of the optimization or the solution of the problem to be zero. Like for instance, if we have, let's say, x1 plus x2, and we are maximizing, then let's say we are going to have an artificial variable in one of our constraints. So constraint, let's say this is one constraint, and we have an artificial variable there to generate that initial solution. However, we know this artificial variable is not part of the problem. So we want to make sure that by the end of the solution, that artificial variable is zero. So what we're going to do is we're going to make that artificial variable part of the objective function, and we're going to multiply that by a very big negative value. This very big negative value multiplied by the artificial variable is going to go against this objective. So our goal towards the end of the optimization is to make this m times r be zero. Because if it is zero, then it's not affecting the summation. So the profit is not going to be impacted by this amount. However, if this m is, let's say, 1,000 and r is equal to 1, then we know that m times r is going to be equal to minus 1,000. So if r is not equal to 0, you are going to be subtracting 1,000 from this summation. So the idea is we use the artificial variables as a way to obtain an initial solution so we can solve the problem. But at the end, we want those artificial variables to be 0 so they don't impact the value of the objective function. So let's look at one example. We have the minimization for x1 plus x2 subject to these three constraints. 3x1 plus x2 equals 3, 4x1 plus 3x2 greater or equal to 6, and x1 plus 2x2 less than or equal to 4. So we want to put this problem into standard form. So using E1 as a surplus in the second constraint and S1 as a slack in the third constraint, The equation form of the problem is given as follows. So we have the minimization of z equals 4x1 plus x2, subject to 3x1 plus x2 equals 3. So that's inequality. So we don't have to add or subtract anything. 4x1 plus 3x2 minus e1 in equals 6, and then x1 plus 2x2 plus s1 equals 4. So we have the problem into standard form. So we set up the initial tableau for this problem. We going to have the following. So for row 0, this is row 0, row 1. So let's say this is row 1, 2, and 3. So the objective function is, or row 0 is going to be minus 4, minus 1, then 0, 0, 0. Okay, so minus 4 is coming from this coefficient, and minus 1 is from this coefficient. Then for the coefficients of the first constraint, we have 3, 1, and then the right-hand side is 3. So these two are 0. Then for the second row, we have 4, 3, minus 1, 0, and 6. And then 1, 2, 0, 1, 4. Okay, so if you look at this tableau, remember that for us to find that initial solution, we are looking for that matrix that looks like an identity matrix. So if we look for example, we have a column of 1s and 0s here. So we know that this S1 is a basic variable. So that's why S1 is listed as a basic variable, and the corresponding location of that basic variable is here, S1. Then you look for the other two columns that are going to generate this identity matrix, and you see that they don't exist. So there's no other basic variable in this type tableau, which was not the case when we had all slack variables. We were able to find those basic variables right away. But in this case, we don't have slack variables for the first constraint or the second constraint. So we cannot state an initial solution right away. So how many variables or basic variables do we have? So by looking at the table, we have just one, which is S1. And how many do we need? Well, we need M equals the number of constraints. So that is 3. Can you easily obtain the basic variables needed for this tableau? The answer is no, we can just find one. Does it work to multiply row 3 by minus 1 to make x3 a basic variable? Yes or no? So the question is, can we multiply row 3 by minus 1? So that will make this negative, a positive. The answer is no, it doesn't work. If multiplying third row by -1, problems turns infeasible because the right-hand side is going to become negative. So we cannot proceed in that way. So what do? We add those artificial variables. When an initial basic feasible solution does not exist, an artificial variable, Ri, greater or equal to 0, can be added to the constraints. It guarantees a starting basic solution. Artificial variables are added only to the constraints with equalities or greater or equal to. The third equation has its slack variable, S1, but the first and second equations do not. Thus, we add the artificial variables R1 and R2 in the first two equations and penalize them in the objective function with MR1 plus MR2 because we are minimizing. So we are going to use positive values to increase the the value of the objective function, which is gonna force the artificial variable to go to 0. So the resulting LP is given as the minimization of Z equals 4x1 plus x2 plus MR1 plus MR2. So if you don't want to think about whether or not you're gonna add or subtract the artificial variables in the objective function, my advice is to refer to this rule that is stated in this slide. So if we go back to slide 9, if you want to know whether you're going to subtract the artificial variable or add the artificial variable, remember that in maximization problem, we're going to subtract them. And in minimization problem, we're going to add them to the objective function. So that's what we are doing here. Since this is minimization, we are adding artificial variables times m to the objective function. And then we have an artificial variable for the first constraint, and we have an artificial variable for the second constraint. For the third constraint, we don't need an artificial variable because we can identify a basic variable using the slack. Since we don't have a slack variable in the first two constraints, then we need to add an artificial variable. So the starting basic solution is now R1, R2, S1, which gave us a value for R1 equals 3, R2 equals 6, and S1 equals 4. From a computational standpoint, solving the problem on the computer requires replacing m with a sufficiently large numeric value. So the question is, what value of m should we use? The answer depends on the data of the original problem. The penalty must be sufficiently large relative to the original objective coefficient to force the artificial variables to 0 in the optimal solution. In the present example, the objective coefficient of x1 and x2 are 4 and 1, respectively. And it appears reasonable to set m equals to 100 because 100 is relatively large when compared to 1 and 4. So 100 is fine. If we were dealing with coefficients of 100 or 200, then maybe we should go to 10,000 for the value of m. So we can go 2 zeros up to the coefficients present in the objective function. So this is the new formulation. So now we can set up the table for this new formulation with the artificial variable. So as we stated, we want to make m equals to 100. So that's going to show up here. So basic variables, sorry. We have z minus 4, minus 1, 0, minus 100, minus 100, S1 is 0, and the right-hand side is 0. And then for the first constraint, we have 3, 1, 0, 1, 0, 0, 3. For the second constraint, we have 4, 3, minus 1, 0, 1, 0, 6. And for the third constraint, we have 1, 2, 0, 0, 0, 1, and 4. Okay, so the question now is, what are our artificial variables? So we need to identify them. So we know S1 is going to be an artificial variable. And we want R1 and R2 to be our basic variables for the initial solution. So we know we are almost there in terms of making this a part of the identity matrix. We need to make sure that these are zeros. So we're going to perform an operation next. But we know that this one corresponds to R1. and this one corresponds to R2. So those are going to be our basic variables. So this is the same table, but before proceeding with the simplex method, computations, the zero must be made consistent with the rest of the tableau. The right-hand side of the zero in the tableau currently shows that z is equal to 0. And that's by looking at this value. Okay, so z is equal to 0. R1 equals 3, R2 equals 6, S1 equals 4. However, given the non-basic solution, x1, x2, x3 equals 0, the current basic solution is R1 equals 3, R2 equals 6, and S1 equals 4, which yields a z equals to 900. So if we look at the the objective function right here, right? So it's 4x1 plus x2. So 4x1 plus x2 plus 100 R1 plus 100 R2. If we substitute the values, these values, into the objective function, this is going to be equal to 4 times 0 plus 0 plus 100 times R1, which is 3, plus 100 times 6, which is R2. So this is equal to 900. So right now that is not shown here. So we need to make sure that if we have a value of R1 equals 3 and R2 equals 6, then to make this consistent, we need to make sure that this value is 900. So that's not showing up. To eliminate the inconsistency, we need to substitute out R1 and R2 in the 0 using the following row operation. So the idea is we need to make this column ones and zeros, and these columns ones and zeros. So if we substitute out, if we make these two values equal to 0, then this right-hand side will become 900. And how do you make those equal to 0? Well, you use the elementary row operations, right? So you can multiply this row by this row by 100 and then add it to row 0. And then you can multiply this row by 100 and add it to row 0. So that's what we're gonna do next. So first, we are going to multiply this, sorry. So this row by 100 and add it to row 0. And also we are gonna multiply this row by 100 and add it to row 0. So if we perform those computations, this new row 0 will look like this: 696, 399, minus 100, 0, 0, 0, and 900. So now we have the identity matrix that we were searching for to identify our initial solution. The result is that R1 and R2 are now substituted out, have a 0 coefficient in row 0 or in the 0 with z equals to 900 as desired. The last tableau is ready for the application of the simplex optimality and the feasibility conditions. The variable x1 having the most positive coefficient in the 0 enters the solution. So we are minimizing, so x1 is gonna enter, has the largest positive coefficient. The question now is who's going to leave? So we need to perform the minimum ratio test, looking at the values of these two columns. So for the first ratio, we have 3/3, which is equal to 1. Here we have 6/4, which is equal to 3/2. And this one is 4 divided by 1, which is equal to 4. So the minimum between 1, 3/2, and 4 is 1. So that means that R1 is going to exit the basic variables. So the minimum ratio of the feasibility condition specifies that R1 as the living variable. So once the entering and the living variables have been determined, the new tableau can be computed by using the familiar Gauss-Jordan operations. So after making x1 a basic variable, as you can see here, after performing the operations to make this column for x1 is 0, 1 column, this is the resulting tableau. The tableau shows that x2 and r2 are the entering and leaving variables respectively. So if you look at the row 0, after completing this iteration, we still have a positive coefficient for x2. So that means that x2 can enter the basic variables. And we can perform the minimum ratio test to identify the variable that is leaving. So the tableau shows that x2 and r2 are entering and leaving. So let's double check that. So we are going to perform the minimum ratio test looking at this and the right hand side. So here we have 1/1/3, which is 3. Here we have 2/5/3, which is equal to 15/3. And then here we have 3/5/3, which is equal to sorry, I think I made a mistake here. So it's 2 times 6. So it's 6 times 5/5, 6/5. And this one is 9/5. Perform this right on. Let me double check these numbers quickly. So let's do the minimum ratio test. Okay, so we have 1 divided by 1/3, which is equal to 3. Then we have 2 divided by 5/3, which is equal to 6/5. And then we have 3/5/3, and this is equal to 9/5. So the minimum is this value. So that means that R2 is leaving. Continuing with the simplest computation, 2 more iterations are needed to reach the optimum. x1 equals 2/5, x2 equals 9/5, and z equals 17/5. So that concludes the explanation of the M method. So again, the idea here is to understand that we will not always find an initial solution for applying the simplex algorithm. So we have explained a strategy that is called the M method to find an initial solution for our problems when you don't have the slack variables to start the simplex algorithm. So for example, when you have equalities or you have greater or equal constraints, then you don't have the slack variables to start the algorithm. So we have explained how to use the M method and artificial variables to find that initial solution and to apply the simplex method after finding that initial solution. Okay, so in our next lecture, we're going to discuss the two-phase method. And so we'll stop here.